Chapter 5, the definite integral. In 5.1, we are going to be estimating areas underneath the curve using finite sums. In calculus, derivatives are only half the story. Derivatives help us calculate slopes of tangent lines and calculate the instantaneous rate of change. What we need is a way to describe how the instantaneous changes accumulated over an interval of time. This is done by investigating areas under curves. With this, the second branch of calculus is born, called integral calculus. What that means is we are going to be looking at the change in time with respect to how different variables are changing. So let's just take up problems for example. A train moves at a constant speed of 75 miles per hour from 7 a.m. to 9 a.m. What is the total distance traveled? Now this is a very easy problem that we can do very simply. We know that distance is equal to rate times time. And so we know that the distance is equal to 75 miles per hour times 2 hours. So the distance becomes 150 miles. This does not require calculus to solve. But this is going to be a nice stepping stone into what we will need calculus for. So let's take that same problem and analyze it graphically. So if we look at here's our chart where the horizontal axis is time and the vertical axis is velocity. We have that we're traveling at a constant speed of 75 miles per hour. So then we know that if we were to highlight the area underneath this curve from the 7th hour to the 9th hour, the distance underneath the curve is then going to be the area of this rectangle. So if we look at this distance right here, which is 2, and this distance right here, which is 75, it turns out that the area underneath the curve is equal to the distance traveled. So if you take 2 times 75, you get 150. So it turns out that if you take the area underneath the velocity curve, bounded by the x-axis, you're going to get the total distance traveled. That's pretty easy. Now here comes the question. What if velocity is not a constant function? So what if the velocity function is not constant? What if we have something that looks like this? Well, the problem is here, if we were to, say, travel from A to B, this rectangle does not represent all the area under the curve. So what we're going to do then is we're going to split up this interval into tiny intervals. As shown here. What this is going to allow me to do is to make rectangles that are smaller, like this, which will represent the area underneath the curve more accurately. And when I divide up these sections, I'm going to divide them up evenly so that all of these are the same, and we're going to call them delta x. Let me show you what I mean by that graphically. We'll say that this is my curve right here, and I split it up into this many intervals. You can see how right here, if I have less of the intervals, the area is not represented very accurately. However, the more intervals I add, the more accurately the area is represented. So this is the idea behind a Riemann sum, is we're going to use these sums of these rectangles to represent all of our area. So we can partition the area under the curve into vertical strips. If the strips are narrow enough, they are indistinguishable from rectangles. When you sum up the area of all the rectangles, you get the area underneath the curve.